Welcome back to the deep dive. Today we are focusing on, well, one of the biggest paradoxes in modern AI scaling. You think about these huge foundational models, trillions of parameters, trained on just staggering amounts of data. They're immense.
Absolutely vast.
Yep.
They represent this massive general knowledge base, but the challenge is, once they're built, they're often just too big and unwieldy to specialize efficiently.
Exactly. So you take this terabit of weights, as some call it, and you try to teach it a very specific new skill, maybe using just gigabits or sometimes even megabits of data.
Right.
And the core tension there, it just feels wildly wasteful, doesn't it? To move every single weight in a, say, trillion parameter model just to absorb an update that's like a tiny fraction of its original training.
That intuition is spot on, and it's really the whole motivation behind parameter-efficient fine-tuning, or PEFT methods.
Right.
And for people actually building things, the most important of these methods right now is probably low-rank adaptation, LoRA.
Okay, LoRA. So let's break that down simply for a second. Instead of tweaking that enormous original weight matrix, the W,
Which stays frozen, yeah.
LoRA adds something much smaller, like a pair of matrices, A and B. These act as a small, specialized adapter.
Exactly. So when the model runs, the original weights W are untouched, they stay frozen, and these little adapter matrices, A and B, get added into the calculation. They hold all the new information you've trained.
That small adapter seems key, because you're only training those tiny A and B matrices.
Right. You're massively cutting down the number of parameters you actually have to train and store.
We know that drastically cuts down on memory needs, which is great operationally. But our mission for this deep dive is really to move past that and ask the big question. Can LoRA actually match the performance, the sample efficiency of doing the full, old-school, full fine-tuning, or full FT?
And that's where the research gets really interesting. The sources we looked at suggest the answer is yeah, overwhelmingly yes, but, and it's a big but, only if you get a few key details right in how you set it up.
Okay, so LoRA without regret is possible, but with caveats.
That's a good way to put it. The data shows LoRA really should be the default choice for most fine-tuning. But maybe let's first quickly cover why it became so popular, even before we talk performance. Just the operational side.
Yeah, good idea. Because it really does solve some major deployment headaches, right? What are the main advantages there outside of pure performance?
Okay, I'd say there are three big ones. First is multi-tenant serving.
Multi-tenant, meaning serving multiple users or tasks.
Exactly. Since the huge original weights stay frozen and shared across different tasks or users, a single inference server, like one GPU, can easily hold many different LoRa adapters in memory at the same time.
So one base model, many specialized personalities on top.
Precisely, and this allows for really efficient batched sampling. You see systems like VLLM and SGLang doing this now. One powerful machine can serve dozens of different specialized model versions simultaneously. That totally changes the economics of deployment.
That's huge for scalability. Okay, what else? You mentioned training.
All right, number two is a much more accessible training layout. Think about full fine-tuning. You need to store the weights, obviously, but also the gradients for back propagation and the optimizer moments.
Optimizer moments. Remind us what those are again.
Good question. So if you're using an optimizer like Atom, which is very common, it keeps track of past information to help stabilize training. Things like a running average of the gradient and the running average of the squared gradient. Those are the moments.
Okay.
They're crucial for making FullFT work well, but they essentially double or triple the memory you need just for the weights. It adds up fast, often needing high precision like float 32.
I see. So FullFT is memory hungry during training. How does LoRA help?
With LoRA, you only need to store the much smaller adapter weights, A and B, their gradients, and their moments. Because you're storing far, far fewer weights overall, the memory footprint for training is dramatically smaller.
Meaning you can train on hardware that's maybe only slightly larger than what you need just for running inference.
Exactly. It opens up training to many more people and setups.
Makes sense. And the third advantage, you mentioned ease.
Yeah, the simplest one. Ease of transfer.
Yeah.
Smaller adapter files mean they're super fast and easy to set up, copy between machines, put under version control, whatever you need, just much less friction.
Okay, so multi-tenant serving, accessible training layout, ease of transfer. Those are compelling operational reasons.
Well, definitely sufficient reasons for its popularity, but now let's pivot to what we really wanted to dig into. The actual output quality. What the sources called the low regret regime.
Right, and this is where it gets really interesting, maybe even surprising. Our sources, looking at experiments with modern models like Llama 3, Qwen 3, on standard instruction tuning datasets, They show LoRA can match FullFT, not just close, but match performance and sample efficiency.
That's the definition of low-regret tuning. For supervised fine-tuning on these sort of small to medium data sets, which, let's be honest, is where 99% of model customization happens, the loss curves for LoRa and FullFT track almost identically.
So using LoRA isn't really a performance compromise in those common scenarios.
Pretty much no. It's not a compromise there.
So when does the compromise finally show up? Where does LoRA fall short?
It really only starts to underperform when the dataset becomes absolutely massive. We're talking settings that look more like the initial pre-training phase.
Okay, like terabytes of new data for fine-tuning?
Yeah, something on that scale. Eventually, the LoRa adapter just runs out of capacity to effectively store all that vast new knowledge compared to updating the entire model. But it doesn't hit a hard wall. It doesn't just fail catastrophically.
What happens then?
The training efficiency just gets progressively worse relative to FullFT. It takes more steps or more data for LoRa to reach the same performance level. But again, for most practical applications, building specific skills into a model, you're almost never going to hit that capacity limit.
Okay, so for most tasks, capacity isn't the bottleneck.
Yeah.
Which brings us back to those key details needed to get parity. You mentioned getting the setup right. Where do we need to apply the LoRa adapter? I remember early on, people often just put it on the attention layers.
Right, that was common wisdom for a while. But the data shows that's actually suboptimal. This is a really crucial engineering insight from the sources. LoRa works best when applied to all weight matrices.
All of them.
Yes, and especially when it targets the MLP layers, or the MOE layers if it's a mixture of experts model.
Okay, let's dig into that. Why the MLP layers specifically? Why are they better for storing this new task knowledge than, say, the attention layers?
Well, think about the architecture. What do the attention layers primarily do? They figure out relationships between tokens, context, information flow,
Okay.
how words relate to each other.
Okay, context and relationship.
But the MLP layers, the feed-forward networks, they're more like the model's computational engine room. They contain the bulk of this sort of stored knowledge, factual recall, the reasoning pathways.
Right.
So when you're instruction tuning a model, you're not just changing how it attends to text. You're often fundamentally altering its stored knowledge and how it reasons.
So if the MLP is like the model's internal library of facts and procedures, that's where you want to insert the new information, the adapter.
That's a great analogy, and the data really backs this up. Experiments showed attention-only LoRa significantly underperformed.
How significantly?
Like an attention-only LoRa using a pretty high rank, say rank 256, meaning more parameters still performed worse than an MLP-only LoRa with a lower rank, like 128, even when they had a similar total number of trainable adapter parameters.
Wow, so it's not just about the number of parameters in the adapter, but where they are.
Exactly. The optimization dynamics just seem fundamentally better suited when you're training those dense MLP layers for these kinds of tasks.
That's a huge practical takeaway for anyone building with LoRa. Apply it everywhere, but especially make sure you hit the MLPs.
Definitely.
Now let's get even more nuanced. You mentioned capacity limits earlier. The sources also looked at how much capacity is needed for different types of learning, right? Specifically, supervised learning versus reinforcement learning.
Yes, and this is where looking through an information theory lens gives a really stark contrast. In typical supervised learning, SL, like instruction tuning, you get a pretty high bandwidth of information back from the data. Meaning, for each example, the model gets feedback based on potentially many tokens. Roughly, you can think of it as getting O number of tokens, bits of corrective information per training example. It's fairly dense feedback.
Continuous feedback, almost.
Okay.
How is reinforcement learning different?
RL, particularly using common policy gradient algorithms like PPO, is fundamentally different. The learning isn't driven by detailed token-level corrections. It's driven by the advantage function.
The advantage function?
Yeah.
That basically tells the model how much better or worse its chosen action sequence was compared to what it expected.
Precisely. And that feedback is incredibly sparse. Often it boils down to just 0.1 bit of information per whole episode, sometimes literally just 1 bit.
Wait, 0.1 bit. So even if an RL episode involves generating thousands of tokens, like solving a complex math problem, the core useful feedback for learning might be as information poor as a single bit.
Yeah.
Essentially, yes, that whole long sequence was good, or no, that whole sequence was bad.
That's the crucial consequence, yes. Because the actual amount of information being absorbed by the model from the RL reward signal is so minimal.
Okay.
It turns out LoRa fully matches FullFT for RL fine-tuning, even with extremely low adapter ranks. The sources tested ranks as low as 1.
Rank 1. That must be a tiny adapter.
It's small, but maybe not as tiny as you'd think. Like, a rank 1 LoRa on Llama 3.18b still has around 3 million parameters,
Yeah.
but compare that to the information being learned. For one complex math dataset RL task they analyzed, the total information gained from the reward signal over many episodes was estimated at only about 320,000 bits.
I see. So even a rank 1 adapter with 3 million parameters has
Yeah.
vastly more capacity than the 0.3 megabits of information it actually needs to learn from the RL process.
Exactly. The adapter capacity, even at rank 1, massively exceeds the information bottleneck of the RL algorithm itself.
That completely justifies using LoRA as the default for any kind of RL fine-tuning, especially for reasoning tasks. Capacity just isn't going to be your limiting factor there.
It simplifies the setup enormously. You don't need a high rank for RL.
Okay, fantastic insights. Let's move now to the really practical tuning advice for builders. What are the concrete rules of thumb for setting LoRa hyperparameters? Let's start with the big one, learning rate.
Right. This was maybe the most consistent finding across all the tests, both supervised and reinforcement learning. The optimal learning rate, LR, for high-rank LoRa is consistently 10 times higher than the optimal LR for full fine-tuning.
Wow, 10 times higher. That's a massive difference. Is that like an exact number or a general guideline?
It's surprisingly precise. The researchers actually fit a multiplier function to find the optimal LR ratio, and it came out to about 9.8x.
Almost exactly 10x.
Yeah, and critically, this ratio held constant regardless of the base model size or its hidden dimension. It seems to be a fundamental empirical constant for how LoRa interacts with optimizers compared to full FT.
That's incredibly useful. It simplifies hyperparameter tuning dramatically. If you have a good LR for full FT for a given model and task.
You just multiply by 10, and you've got a very strong starting point for LoRa.
Okay, that's rule 1. 10x LR. What else? Does the rank itself affect the learning rate?
Interestingly, not as much as you might expect, especially early in training. The original LoRa formulation includes that scaling factor, alpha over R, where R is the rank.
Right, I remember seeing that.
Well, that scaling factor is actually designed quite cleverly. Its effect is to make the optimal learning rate approximately independent of the rank you choose.
Ah, so you can change the rank, changing the adapter capacity without necessarily having to do a whole new sweep to find the best learning rate.
Exactly. It decouples rank from LR tuning, which saves a ton of compute and iteration time.
Very neat. Are there any hyperparameters where LoRa is more sensitive than full FT?
Yes. One area where there is a difference is batch size. It seems LoRa is less tolerant of very large batch sizes compared to full FT.
Less tolerant, meaning the performance gap between LoRa and full FT gets wider if you use bigger batches.
That's what the data suggests. The performance gap grows persistently as you increase the batch size.
Any idea why?
The hypothesis relates back to the parameterization. LoRa uses that product of matrices B times A, BD dollars. The optimization landscape for that kind of factorization might just behave differently. Maybe it's more sensitive to the noisier gradients you get with larger batches compared to optimizing a single full-weight matrix dollars.
Interesting. So smaller batches are generally better for both, but the penalty for going large is higher with LoRa.
That seems to be the case, yes. Stick to smaller batch sizes where possible for optimal results with LoRa.
Good to know. Okay, finally, let's talk efficiency in terms of raw compute. We know LoRa uses linear memory, but does it actually save us floating point operations, FLOPs, during training?
Yes, it does, and it's quite significant when you analyze the forward and backward passes, which dominate the computation.
How does it break down?
Okay, for a standard weight matrix in full FT, updating it involves roughly 3n, 2n, 2 multiply-add operations per pass, where n is the hidden dimension.
3n to a 2, got it.
With LoRa, you're freezing the big $1 times no matrix $2. The forward pass still involves multiplying by W, which is 2 under 2 LRPs, matrix vector multiply, but the backward pass only needs to compute gradients for the small $8 matrices. Updating them takes roughly 6 NOOPs, where R is the rank.
So the total for LoRa is roughly 2n, 2 annotations from the frozen W, plus 6 arrays for updating A and B.
Exactly. And the key here is that the rank $3 is usually much smaller than the hidden dimension none dollars. Often $3 is like $64 or $128, while nullers might be $40, $96 or more.
So that 6 array area is tiny compared to the 2 and 2 terms.
Right. For practical purposes, you can almost ignore it in the comparison. So you're essentially comparing 3 N2 2 LLPs per pass for full FT to just slightly more than 2 N2 N2 LLPs per pass for a LoRa.
Which means LoRa uses roughly 2/3, a bit more than 2/3 of the FLAPs per pass.
That's right, a reduction of almost 33% in the core computation per step.
So even if LoRa sometimes needed slightly more steps to converge, which it often doesn't for typical tasks, the compute cost per step is significantly lower.
Precisely. That 33% FLOPs saving per step often means LoRa is more compute efficient overall, leading to faster training in terms of wall clock time and cost. It's a major quantifiable saving.
Okay, this deep dive really paints a clear picture then. Let me try to summarize the main takeaways for you, the listener. Basically, LoRa should probably be your new default choice for almost all post-training scenarios, like instruction tuning or RL fine-tuning.
BSOA, yes.
And to get that true parity with full fine-tuning, what we call the low-regret regime, the really crucial steps are: 1, apply LoRa to all the layers. Don't just stick to attention. Make sure you hit those MLP or MOE blocks.
Absolutely critical.
And 2, use that much higher learning rate, consistently about 10 times higher than what you'd use for full FFT.
Get those two right, and you're likely to get full FFT performance with LoRa benefits.
That covers the practical side for builders.
Yeah.
But you mentioned this research opens up more fundamental questions, too.
Yeah, definitely. On the research side, the empirical success is solid, but it raises questions. For instance, we still lack a really satisfying theoretical explanation for why that 10x learning rate ratio between LoRa and FullFT is so consistent.
It works, but we don't know the deep mathematical reason why it's always 10x.
Pretty much. It's a robust empirical finding searching for a theory, and there's also ongoing work trying to sharpen our predictions about capacity limits. Like, how can we better estimate the actual number of bits required for a model to learn a complex supervised task? It's clearly less than just memorizing the data set, but how much less?
Estimating the true information content of a task.
Right. And people are also actively investigating LoRa variants, things like PISA, and figuring out the absolute optimal ways to configure LoRa when you're dealing with those complex mixture of experts layers and their routing mechanisms. It's a really fast-moving field.
It sounds like it. So wrapping up, all this empirical data, especially that finding about RL needing such incredibly low adapter capacity, it really forces us to rethink some fundamentals, doesn't it?
I think so.
If a model only needs, say, a 1 bit per episode to successfully learn a complex reasoning task via RL, it makes you stop and consider. How much information does a sophisticated neural network policy actually need to absorb to internalize and execute high-level skills or decisions?
Yeah.
That feels like a question that goes way beyond just fine-tuning techniques, gets closer to the core of how we think about learning and intelligence itself.
Yeah.
Something for you to ponder.